Hello everyone, welcome to our channel Code with Sunny, and in this video we will be talking about the fourth problem of bi-weekly contest 72 of Leetcode, and it is the hard problem, right? And the problem name is count good triplets in an array, right? Okay, so before moving on, if you guys are unaware about the Fenwick tree or the ordered set, in C++ there is a policy based data structure ordered set we are going to use in this problem. Okay, and if you are not a C++ programmer, no need to worry about. You have the option of Fenwick tree, an efficient data structure that helps in finding out some certain sum or updating out some certain value in logarithmic time. So yes, Fenwick tree is going to help us in this problem. So if you guys are unaware about this term Fenwick tree, no need to worry about. I will be also sharing the article of Fenwick tree that is present on the CP algorithms website. In case you haven't studied about that, then you can refer to the article that I will share in the description section of the video. Okay, so before wasting our more time, let's begin. We have been given two arrays, nums1 and nums2. Both are following zero-based indexing, and both are of length n, and both contains the values which are the permutation of first n whole numbers, that is the numbers starting from 0. Now a definition of good triplet is being given over here. Like, I will recommend you guys to read this entire definition 2 or 3 times, and if you are still getting the doubts, then no need to worry about. Again, I will explain this entire thing good triplet with the help of examples and analyze, and will help you to analyze the entire thing, what is actually the meaning of this good triplet and how we can find them efficiently. So yeah, I will explain this later on. For now, let's skip it. Yeah, we need to return the total number of good triplets, which should be our answer. So let's look over the constraints. N max is going to be around 10 raised to the power 5. So n square solution will obviously fail. So in the best case, we would be looking for O of n into some log factor, logarithmic time, which would pass all the test cases efficiently. Okay, so let's look out the definition of the good triplet. Okay, so what I'm going to do is, so let's pick out the same example, 2013. So this is the very first array, and we have the another array 0, 1, 2, and 3. Okay, so a good triplet is that triplet. Uh, let's say we have the triplet A, B, C. So ABC is called a good triplet only and only when the values denoted by A, B, and C. Let's locate that values in the array A1 and in the array A2. Let's locate the values. Okay, so you can see that index of A. So I can write down index 1 of A. We have some, it will give out the sum index. Let's say A is 1. For an instance, let's say A is 1. So index of the value 1 will be, you can see, 2. If you consider 0 based indexing, 0, 1, 2, 3. Index of the value 1 is 2, right? So this is what I want to say. So index 1 of A we would be having, and we would be having index 1. 1 denotes the array of B, and also we would be having index 1 of C. Okay, so the definition says that the triplet ABC is good if the index denoted by, that is the indexes where these values are present, must follow a increasing order pattern. You can see this is actually the increasing order pattern, right? So this should be like increasing. So and this is not only the sufficient criteria of good triplet. So there is an and condition also, and index 2 of A must be also less than this B, and this should be also less than C. The only difference over this is like we are operating on the different arrays. So a good triplet ABC, like a triplet ABC is called a good only when the for the respective arrays the indices must follow in an increasing order fashion. Okay, so you can see if we pick out 0, 1, 3 over here. Okay, so 0, 1 and 3. So for the A1 array, the indexes are, you can see 1, 2 and 3. Right, and for the A2 array, indexes are 0, 1 and 3. You can see they both are in increasing order. Right, so let's also pick up another example. Uh, yeah, 40132. So let's me move out to the next piece. 40132. So this is for the array A1, and we have another array A2. 41023. 41023. Right, so let's pick out the same thing. Let's say we have 403. So we have the values A as 4, B as 0, C as 3. That is, we have the triplet 403. Let's check it out whether this is a good triplet or not. So for case of A1 array, so 4 is present at 0 index, and 0 is present at 1 index, and 3 is present at 3 index. So we have the pair as 0, 1, 3. And for the case of A2, 403, let's locate 0, 2, and this is nothing but 4. So for case of A2, it is nothing but 0, 2, 4. Note that both the arrays, this one and this one, the set are in increasing order. So this is a valid triplet. Right, so let's also take another triplet and check it out. Like let's say we have taken 1, 2 and 3. Okay, so you can see from this array A1, I will get the index as 2, 4 and 3. And for the A2, we would be having what? The indexes of this 1, 2, 3 values as 1, 3 and 4. Okay, now let's check it out whether both the array of indices are in increasing order or not. Now this is not in increasing order, this is in increasing order. But according to the definition of a good triplet, both should be in increasing order. So this 1, 2, 3 is a bad triplet. Okay, so I think the concept of like the definition of good triplet is clear. So let's focus upon how we can solve this problem efficiently. Okay, so we are going to operate on the same example. So like we have a pair always, like we have a triplet always ABC, and in more general problems involving triplets, the best way is to fix this middle number. Fix it. Okay, so let's say we are working upon this array A1, and we are always fixing the values over here. That is, we are fixing 0, or we are fixing 1, or we are fixing 3, right, or we are fixing 2. Means B can become 0, B can become 1, B can become 3, B can become 2. So by doing that, we have a choice, our entire search space will be reduced only to A and only to C. So this gives us a more hint and idea to solve the problem efficiently, right? Yeah, so by fixing, let's say we have fixed this b over here. Okay, so let me write down. What I have said is we have some value over here, we have b over here, and we have some value over here, but this b is fixed. B is fixed is now 1. Okay, note that we have this triplet. Okay, right. When we fetch out the indexes, you can see index of 1 is actually what, 2. And since this triplet we are working upon the array a1, we will always make this triplet good only for array a1 right now. So this whatever the values that will be contained over here, c values, must be lying over the right side of this index of b, that is must be among these values. Similarly, this a values must be any values among this left side of this one. Okay, so let's consider the a values and b values. Okay, so first let me change out the color. So the a values are 4 and 0, and the c values are 3 and 2, right? So when we choose any triplet, it can be of like 4 2 sorry 4 this is actually b is 1, right? So it becomes 4 1 2, or it can be 4 1 3, or it can be what, 0 1 3, or it can be 0 1 2. There are 4 possible ways to choose this triplet. Okay, so we are not interested to do that. Okay, so for now you can see we have fixed this value of b. Now let's try to fix the value of b is 1. Let's try to fix its position in array a2. Okay, so when we try to do that, you can see this is the position we have got right over here. So when we got this position, we are also dividing this array a2 in two sets. The a values, let's say a dash values, and again this is again a b dash values. Not calling it as b dash because it may confuse c dash values. Okay, so it means that when we want a triplet to be good, we will choose some element from here and some element from here. And for a triplet to be good, these, when we choose these indices must be a part of this a dash values and c dash values also. Like suppose we choose 4 over this a values, then 4 must be present in a dash values also. And for over here, let's say we have chosen this 2, then 2 must also be present in c dash values, right? Suppose this happens, so it becomes 4 1 and 2, right? So this is a triplet. So you can see the for a1 the indexes will come out to be 0 2 and 4. This is in increasing order. And for a2, according to this triplet, the values will come out to be 0 1 and 4. Sorry, it would be 3. And this is also in increasing order. So it means that this triplet is good, right? Okay, so what I want to say is, like, to make the triplet good, we will fix this b, and when we fix this b, for the array a1 we have a values, that is the left set, and we have the c values for the right set. Now to make this triplet good, these values, a values and c values, must also be present over this array a2 also, when we divide this into two sets, a dash values and c dash values, according to the position of this value b over this array a2. Okay, so let's say we are going to name this, that would be better. So let me first, so this is actually L1, this is R1, and this is L2 set, and this is R2 set. Okay, so our triplet count, so our count of triplet will increase by number of elements, let's say the count of elements which is present in the intersection of L1 and L2 multiplied by count of the number of elements that are present in R1 intersection R2. Okay, so yeah, you can easily see that when we fix like this count is for when fixing the value at 1. Let's say when we fix the value at a specific index. Okay, so I will write it down in general case count of I. Yeah, so this is for the not calling it as it would make more complex. So this is actually the total answer. So this is the total answer. And this part that you are going to see, we are going to do this for every index. Like when we fix B over this position, we will calculate this value. And when we fix B over this position, we will calculate this value. And we will try to add all these values by iterating over this entire array A1. Okay. Now let me just explain why this formula, like this formula in a detail I want to explain. Like when we find a number of elements L1 intersection L2, we would be always having some element which satisfy the positioning in A1. Like if we choose 4 and if we choose 2, you can see we have the pair like 4, 1 and 2, and both index are in increasing order, right? 4, 1, 2, you can see. And when this when we, let's say this intersection will give the values as 4, 1, 2, and when this values will locate in this array A2 4, 1, 2, this is also in increasing order. It means that when we partition the set with respect to the position of B, and by maintain the and find out two different sets A dash, C dash, and similarly A values and C values, and find out the intersection, we will have all those triplets, right? And their count of triplets will be incremented by number of intersection in L1 and L2 multiplied by number of intersection in R1 and R2. Okay, if you look out the answers for this case, you can see it is like when we fix this one, we have 4 3 and 4 2, right? So when we fix this one, you can see I can have 4 3. You can see when we fix 4 3, it would be having like this 4 1 and 3. Again, these are also 4 1 and 3 present in increasing order. Okay, now the thing is, how do we find this count L1 intersection L2 into count R1 intersection R2 efficiently? Note that this answer should be done for every index, so it would automatically take O of n time. But to do this operation, we would need a efficient data structure that would work in logarithmic time. We'd be using Fenwick tree. Okay, so how do we do that? So let's try to understand. So let me first erase this all. Okay, I will not erase this one. Let me erase this one also, because I need to explain. Okay, so let's begin. So what I will do is, like, first I will locate like the position of the elements over this position, over this array A2. So I will maintain another array called position, where it will do like position of some value nums2 of I will be exactly equal to I. So 4 will be placed at this position, 0, and 1 is placed at this position, 0 is placed at this position, like mapping of number to index. We will do that. Okay, and the next step would be, let's say we are going to have this 1, so it will locate the value at this one, and we have these two sets 4 0 2 3, and yeah, and here also we have 4 0 and 3 2. So we need to find the intersection of these sets. Okay, so what I will do is, like, when we are at this position 1, we have already done with these positions, right? So let's try to locate the values of 4 and 0 in the case of this A2 array. So position of value 4 in this array A2 is 0, and position of number 0 in this array A2 is, you can see at this position, the index is 2. Okay, note that I am working upon this value 1. When we are working upon this value 1, this set has been utilized. It means that we are already find out the position of all this 0 and 2, right? The position of 4 is 0 and 0 is 2 in array A2. Okay, now we will also check it out, the position of 1 in this array A2, which is, you can see at position 1. So 1 is present at this position 1, and you can see we have this array at this position. So it will divide this array 0 2 into two parts. Like it can be like it can be also happen, like it can also happen that it will divide the array like this one. The entire 2 part would come over left and a 0 part come over to the right, or it can also happen like nothing goes to the left and the 2 part goes to the right. But here in this case it is dividing these two parts equally, so this will automatically become the left set, right? And this part is of no use for us right now. So you can see this is actually matching, like this index which is present over here is 0, and this is denoting 4, the value 4, and the actually the index is 0, which is actually denoting the value 4 over here. Okay, so it means that when we take a 4 in the left set, it will make valid. Okay, now we can do this search efficiently with the help of Fenwick tree. Okay, so we will query this Fenwick tree over the position 1, and we will count down number of elements which are less than the number 1 in this array when we locate the position of 40 in this array A2. Suppose we are at this position 2. So we will locate the position of 4, pose of 4. We will locate the position of 0. We will locate the position of 1. We will locate the position of 3. Now we all have these data in the Fenwick tree, and then we will query the position of 2, which will give us number of elements which are strictly less than this value. And when we got that value, that value would be the left set intersection, which is nothing but the answers that we have over here, that is this count L1 into L2. And similarly we can do that for the suffix part also, right? And yeah, for this case, number of elements, let me write down number of elements less than or equal to a given number, like not calling that equal to right now, it may confuse, less than a given number, a number can also be efficiently calculated with the help of ordered set. I will show you both the codes. There's not much difference. The main, you should understand the idea that when we try to locate the any number to in the array A2, it will divide the array into two sets. And how to find the intersection? So we will query the current position in the Fenwick tree, and it will give you the number of elements which are less than this value. So this will be the left set intersection count. And similarly we can do that for the suffix part also, which will give us the right set intersection count. So let's move on to the coding part. How we will do that? Okay, so first let me show out you the ordered set code. Okay, So this is the thing that we need to include when we are working with the ordered set. Okay, so first, as I've already said, we will map all the numbers with their indices for the array 2, that is nums of 2. We will take the ordered set and we will try to fill up the prefix and suffix separately. So this for loop will be the prefix. So we will first find out the current position of the current value, which is current value is nums1 of I, and position will give you the value will give you the position of nums1 of I in the array A2, in the nums2 array. Like first we'll get the value, then we'll find this value, the index of the position of this value present in the another vector, that is nums of 2. And when we got the position, we'll find out the intersection, that is left set intersection for this array A1 and this array A2, considering the current value nums1 of I as the middle value in the triplet. How to find the you can see the intersection part, since we have already got this ordered set will store the positioning of numbers, right? This ordered set will store, suppose let me first erase all those, it is so much clumsy type. So ordered set will always store the position of numbers, right? Suppose we are working upon this 3. Suppose we are working upon this 3. It means that ordered set have already stored these values. So ordered set will store position of 4, ordered set will store position of 0, and ordered set will store position of 1 in a sorted form. So position of 4 is what? In the array A2 is 0, and position of 0 is 2, and position of 1 is 1. But this is not the sorted form, so ordered set will store like this one. Okay, so this was for the 3. And what is the position of 3 in this array A2? Position of 3 in this array A2 is the last one, which is the 4th, right? So we will ordered set will query what is the number of elements which are strictly less than 4. So it will give us this entire thing. So this is actually the left set. Similarly, you can do that for the right part also. So prefix of I will store this number of elements which are less than this current position, and we will insert this current position after this is done. Similarly, we are going to do that for the suffix part. Note that the number of indices which are strictly greater than the current pos we need to maintain, which is actually set size minus this s dot order of key. We will insert it back, and our answer will be the number of pairs for left set count into right set count, considering every fixing every value of b over this entire array. So I1 up to n minus 1, you can see pref of I into sub of I will be our current answer, and it will be incremented for every position of I from 1 to n minus 2, both inclusive. So this was the ordered set based code, and let's look out for the Fenwick tree. There doesn't any much difference, you can see. Yeah, so this is about the Fenwick tree, get function and update function. Okay, so let me show you one thing more. You can see this part is exactly same once we calculate pref of I and sub of I. So the only difference is how do we calculate this pref of I and sub of I. So you will use a one based indexing, bit pref and bit sub. So like it will help in updating and getting the answers. So yeah, first we will find out the position, and we will query in the Fenwick tree number of indices in the set which is strictly less than the current position. It is for the prefix one, and similarly after doing that we will update it similar to the ordered set where we will inserting the value. And here is the suffix one, we will be doing the same thing. Since we need to find the greater number, like number of indices in the set which are strictly greater, we will subtract the number of elements which are smaller from the total number of elements that are still like the currently total number of these amount of elements are considered, and this amount of elements are smaller, so we will subtract it. And yeah, our answer will be incremented by for every count satisfying this prep of I into sub of for every index we are trying to fix the current value of b. So this will give you all test cases passed. So if you guys have still any doubts, do let me know in the comment section of the video, and thank you for watching this video.